Nice. Okay, moving on to chapter 8, the second biggest chapter in our syllabus. I am going to have a hard time with this. Okay, I'm going to merge chapter 9 and 10 together because chapter 9 and 10. Okay, no. All right, yeah. I'll merge chapter 9 and 10 together. It's big, but nothing to do. Okay, all right. Chapter 9, 10. Magnetic field and alternating current. Magnetic fields and alternating fields and alternating current. No, okay, if I merge this, okay, merging this might make it the biggest chapter in the syllabus, or at least in my notes. But yes, even though it is large, it's still concise compared to what you guys. This is going to be very big, so stay tuned, guys. Okay, wait. Not this big. I feel like this should be good. Yeah, this is good enough. This is very good. Like I know a lot of people. Uh, okay, yeah, this is good. This is good enough. Okay, let's start with our definitions and small questions and long repeated questions. Okay, so number one is Lenz's law. So what is Lenz's law? Induced EMF acts in such a direction that it opposes it opposes the change causing it. Number two, Faraday's law. Faraday's law states induced EMF is directly proportional to rate of change to the rate of change of magnetic flux linkage. Okay, number three is Tesla. Tesla is flux density that causes a force of 1 Newton on a 1 meter wire carrying a current of 1 ampere perpendicular to magnetic field. Perpendicular to magnetic field. Number four, ideal transformer. Ideal transformer is a transformer where there's no power loss. Okay, so I can just write no power loss in transformer. In transformer. So input power is equals to output power. Equals to output power. Next, number five is smoothing. Smoothing is output potential difference does not fall to zero. Okay, number six. How is EMF induced in a coil? Okay, this is there are things to answer this in bullet points. Okay, that is move coil towards slash away from solenoid, vary current in solenoid, and finally rotate coil. Okay. Number 7, magnetic field is a region of space where a current carrying conductor experiences a force. Number 8 is sources of power loss within a transformer. Within a transformer. That would be heating due to eddy current, number 2 is heating due to current in resistance coils. And finally, number 3 is loss due to charging. Loss due to charging. Okay. Number 9. Number 9 is magnetic flux, which is product of flux density, and area, where area is perpendicular to magnetic field. Okay. Number 10, magnetic flux linkage. So the magnetic flux linkage is magnetic flux density into area into number of turns on coil, number of turns on coil, where area is perpendicular to magnetic field. 11 is situation in which a charged particle in the magnetic field does not experience a force. Okay, so that is, there are 2 bullet points where a particle is stationary or particle is moving parallel to magnetic field. Nice. Okay, to further down this. Number 13 is okay. N is equals to number density of charge carrier, T equals thickness, and Q equals to charge on each charge carrier. 14. Magnetic flux density. This is force per unit length and per unit current, where current slash length is perpendicular to magnetic field. Okay, I think we got a lot. There's a lot more. I don't think we don't have space, so we have to make more space. It should be good. Okay, so moving on to number 15. Okay, conditions for a wire in a magnetic field to experience a force. So what are the conditions? Again, this is also a repeated question, which we must write in bullet points. That is, there must be current in the wire. And number two is, wire must be at a non-zero angle. Okay, six more, I think, to go. And then we have, I think, three more long concepts that go in the definition and SAQ section. So overall, nine more things left to write. So I know, guys, it's getting exhausting, but I hope you'll be patient with me. Okay. 16 is rectification. Okay, rectification is conversion from AC to DC. From AC to DC. Okay, 17. Half wave rectification. So half wave rectification is voltage in one direction is removed. Voltage in one direction is removed. 18. Full wave rectification is voltage in one direction is reversed. Okay, done. 19 is, sorry, let's write this nicer. Nicely, 19. Frequency of an alternating current. Okay, so it is number of cycles per unit time. Number 20 is, right, yeah. Number 20 is RMS value. RMS value of an alternating voltage. Oh, sorry, of an alternating current. So this is the value of a constant current that produces same power in a resistor as the alternating voltage. 21 is, yeah, 21 is RMS value of RMS value of an alternating current. Sorry, of an alternating voltage. This is literally the same definition, but we change current to voltage. Okay, so we basically write the same thing, the value of a constant voltage that produces the same power in the resistor as the, right, it's a mistake here, as the alternating voltage. Right. So still have some space left. No, we have good space left. Okay, let's get to it. Hmm. Okay, now some repeated 3 to 5 more questions that come in in the questions of magnetic fields. So let's go. Let's go through them one by one. I think there are a total of I think 6, if I'm not wrong. So one is, how is a particle undeflected through a magnetic field? Through magnetic field. Okay. The answer is 1. Okay. Particle experiences a force up/down. Electric field is generated down or up, which generates uh, an electric force opposite to magnetic force. Number 3, in turn, particle is undeflected when uh, so okay, so particle is undeflected when magnitude, sorry, excuse me. Don't know how the color changed. Right, okay. I'll zoom it for, okay, yeah. Yes. When magnitude of electric and magnetic force are equal. All right. We're moving to 23. This question is kind of related to gravitational fields, but it came in the magnetic field chapter. Why gravitational field of Earth does not vary around the surface? Okay. The answer to this is lines are evenly spaced and they're pointing down towards the surface at all times. Okay. Sorry, at all points, my bad. At all points. Okay, next is 24. How magnetic field varies around a surface of Earth, the surface of Earth. So this is also in bullet points. And I encourage everyone to write it in bullet points in the exam. It's fine if you write it in sentences or in paragraph, but bullet points make it easier for the examiner to mark you. So Number one, it's strongest at the poles. Two is weakest near equator. Three is it's perpendicular to surface at poles. Finally, it's parallel to the surface near equator. Okay. Number 25 is wait, what's that? Principle of magnetism. Principle of magnetism. This was most probably a 5-mark question, if I can remember it. Okay, so what is the principle of magnetism? Yeah, this is a very big one. When two solenoids are placed side by side with their terminals connected, that's bullet point 1. The magnetic flux linkage changes and an EMF is induced. Point 3 is a current is therefore also induced, uh, thus producing their own magnetic field. Point number 4 is therefore both solenoids exert a force on each other, which is either attractive or repulsive. Number 5. Okay, now you have to understand this concept very carefully. Now, the force will be attractive if you pull them away. Pull them away. Okay. And it will be repulsive if you push them together. This is due to Lenz's law. Due to Lenz's law. Finally, number 6. Mention other concepts like uh, eddy current. By the way, don't write this. Wait. When I mean mention other concepts, I mean some questions are point specific. So you have to talk about either the change in magnetic flux linkage and what it does, what effect it has, but you can also sometimes mention things like eddy current. Okay, so I'm just crossing this out so you don't get the you're not misinterpreting. This is just for me. Okay, all right. So moving on, eddy current. Wait, what was I gonna say? Okay, yeah, eddy current is generated, therefore causing magnetic break. Therefore causing magnetic break. So this happens when change in magnetic flux occurs due to change in displacement. Okay, there is one more point that I'd like to mention. Oh, by the way, hold on. I won't end the bullet point here. So continuing from this, therefore causing magnetic break, which makes oscillations damped. Now, this is a concept that I forgot to mention, but I will right now. This is actually in a simple harmonic motion chapter. Right. Right. So, right. Right, excuse me. So we have something called number 9. This is damping. So there are 4 types of damping. Number 1 is light damping. Number 2 is heavy damping. Number 3 is critical damping. Number 4 is over damping. Okay, now to explain, well, I'll explain it very uh, nicely. Okay, so these are 4, right? Now if we draw, like, can we draw it? No, take some time. Actually, I'd like to do this here. Nice. Okay, so okay, there's a diagram if I'm not wrong. Okay, guys. So right. So basically, again, we have to draw a graph, right? Let me try to see if a shape works. Oh, this is not good. I don't like this. Okay, I'll just draw it freehand. Guys, if anyone is an expert in working with Microsoft OneNote, please be very happy if you guys left a comment on how can I use my tools more effectively. But yeah, let's just draw the graph. Okay, right. So this is displacement. Okay, so what is that? So the few types of damping are. Okay, let me show you. Yes. Okay, so this is right, my bad. So very bad drawing. First, let's draw this. So this is known as light damping. This is critical damping, and this is heavy or also known as over damping. Right. So I'll just label them. So this one is light damping. This is this is critical damping. This is over damping, or sometimes also called heavy damping. All right. Okay. So these are the 3 types of damping. You just have to know the basic idea. However, there is something, I think there is calculation for light damping, but that's for your mark scheme and question paper and other people to explain. That's for a teacher to explain, not for this. Okay. But if it comes to drawing, you guys should be fine. Okay. Now we go back to our magnetism chapter. Okay. So this was number 25. Okay. What else is left? Okay. Yeah. So since I spoke about eddy currents, luckily for you guys, the next concept is regarding eddy currents. Okay. So eddy cur okay, wait. Okay, so we have eddy currents. When they the actual question is very long, but the main idea of the question is eddy currents when they happen and concept and other concepts. Okay. Now this is okay. Let's say okay when a pendulum or metal sheet is swung is swung across 2 poles of a magnet, or when a magnet is or when a magnet is moved between a solid the object. Okay, so what are the object? Which object am I referring to? The objects are pendulum, metal sheet, or magnet. Okay, the thing that is moving. The object cuts the magnetic flux, causing an EMF to be induced. Number three, uh, induced EMF causes eddy currents that generates heat and causes resistive forces uh, leading to damping in the motion of oscillation. Number four, finally. Now, this is also known as electromagnetic break. Okay, 27. We have two more concepts and then we will be done. Actually, no, we have one concept left. Now, this is 27, I think, yeah. This is the biggest one so far. How a Hall voltage develops. This is also called origin of Hall voltage. Okay, so for this I have to draw a diagram, actually. No, hopefully, do we have time? Yeah, we have time. Hopefully I can finish it within this. Okay, so, right. Now, let me first draw the diagram and then I'll explain everything. Okay. All right. First, okay, so this is going to be positive. Okay, let's label label the sections. This is A, B, C. This is D. This is E, F, G, H. H is the top part. G is also the top part. D is the bottom part. EF is also the top part. A is the bottom part. Okay, so okay. The one thing that I missed is okay. That was kind of bad. Draw a voltmeter across this. Okay, the voltmeter. Now, similarly, I also have to draw. Okay. Similarly, to draw a circuit. Okay, wait. Draw this along. Okay, my bad, I made a mistake. Okay, just you guys should draw this with me, all right? Because I think I was doing it fine. Oh, there's a battery here. No, actually, stick. Battery here. Okay, so the battery positive terminal, negative terminal, ammeter. Okay, there's a current flowing in this direction, current flowing in this direction, and so on. So this is positive charge. Okay, conventional basically. Okay, now things that we will be given are current current flows from ADHE to PCGF. Magnetic field is from ABCD to EFGH. This magnetic field is usually given. Okay, now using Fleming's left-hand rule, using Fleming's left-hand rule, we find okay that direction of force is towards ABFE. So positive charge accumulates on ABFE. Thus, electric field is established between them. As you can see, negative and positive charges, right? Okay. Sorry, it's not between them, between, wait, let me see. Let me write it. Between ABFE and CDHE. CDHG, right. So, when magnetic force is equals to electric force, charges are undeflected and move in a straight line. Right. So this is a summarized version, but if you were to write it in words, there are a few things that you have to mention. So the Hall voltage apparatus, HV apparatus, has 6 sides. 2 sides connected to battery, 2 sides connected to a voltmeter. Okay, then last 2 sides are exposed to magnetic field. Number 4 is the switch is closed and current flows in a direction indicated mm, okay, yeah, current flows in the direction that is indicated, right? Number, sorry guys. Okay, so where was I? Right. Okay, all right, excuse me. So point number 5 was direction of magnetic field is determined from question. Now, what does this mean? This means that either it is given in the question or you are given the 2 other directions. You're given the north and south poles and the direction of the current, and you have to use left-hand rule to find out the direction of the magnetic field. Okay? All right. Sorry, actually, no, the magnetic field is given. You have to use left-hand rule to find, okay, sorry, I messed up. Direction of magnetic field is north and south. So it is always, it's most of the time given in the question. Or you have to use, okay, no, I was right. Yeah, you have to use Fleming's left-hand rule. Okay. Now, using left-hand rule, we find the direction of magnetic force. Magnetic force. Right. Well, I don't need more lines. I'll just need till this part. Okay, thank you. All right. So Okay, so using left-hand rule, we find the direction of magnetic force. All right, or sometimes given in question, unless it's given in question. Point number 7 is a repeat of the last points in my summary. That is, electric field is established opposite to magnetic field. Point number 8 is at one point, magnetic force is equals to electric force. Then particle moves in a straight line. Hence, which leads to point number 9, that the particle is undeflected. Undeflected. Nice. So that's all. With this, we are done with the definition, past questions for magnetic fields and alternating currents. Now we move on to our concepts. Stay, be patient, guys. This is the biggest chapter in your A2 syllabus. So of course, there is going to be shenanigans. It's going to be long. And again, you can do nothing other than sitting down and listening to it. So, right, number 1 is how to find the magnetic field around a current carrying conductor. Okay. Using the right hand grip rule. No, actually, this makes it darker. I want something lighter. Okay. This. Nice. Okay, this looks nice. So, the current carrying conductor. So this is the wire. Okay. Current is flowing upwards. Hence, the magnetic field is something like this. So it is this. All right. This is the field. So it's a straight wire. Straight wire. Thumb is towards current, the direction of current. Curl of fingers is the magnetic field. Now, if I were to draw it, it would be something like, excuse me for my bad drawing. This is, oh wait, sorry. This is your thumb. These are your fingers. 1, 2, 3, 4. And so here goes your arm. Okay, so add a little bit of detail. The nails. Okay, so this is your thumb, and this is curl of fingers. Nice. Okay, all right. Then for a coil of wires, or what we call a solenoid, it is, wait, okay, it is, so let's draw a solenoid. So this is the north, this is the south. Nice. Okay, and there is circuit, or energy. Current flow is in this direction, this direction, this direction. We know the magnetic field is from north to south. Okay, so then your arms will look something like this. 1, 2, 3, 4, and 5. Okay. 1, 2, 3, 4. 1, 2, 3, 4. So this is the current. This is north. Okay. Right. Okay. Okay. Nice. So it's basically the opposite for this one. For this one, your thumb is field and curl is the current. Nice. Okay. Concept number 2. It is going to be force on a current carrying conductor. Okay, the force on a current carrying conductor. So let's say this is the north. Let's say this is the south. Okay, then magnetic field, current, force. All are perpendicular. All are perpendicular. Now, how does a particle behave when it's placed near north and south poles? Let's check it. North, this is south. Okay, so 1, 2. This is particles going into the page. So for a particle going into the page, the direction is kind of something like this. For into the page, your fingers point downwards. Your thumb points downwards. Your curl of fingers is towards going right. So try it yourself. Okay, right. Therefore, we can say the particle faces the force below, down. Now, how can we find this? What's the law? The law is, or the method is Fleming's left-hand rule. Fleming's left-hand rule. Okay, so your fingers, so your thumb, your first finger, and your second finger. 1, 2, 3, 4, 5. Okay. Actually, let me try it nicely. Because the other fingers are curled, right? So they are going to be like this and this. Okay, so, right. Right. So this is your, so all of this are 90 degrees to each other. Okay, they're 90 degrees to each other. Your thumb will always represent, the force, the direction of force. Your, your first finger will represent the direction of the field, north to south, or into the page, or out of the page. Into the page is towards the page, out of the page is just coming out of the page, right? And this is the direction of current, positive to negative, or plus Q to minus Q, right? I'll just write it down in words as well. Thumb is force F, first finger is magnetic field, B, or into page, out of page. Second finger is the direction of current, I, positive to negative. Okay, so these are the few concepts that you need to work with magnetic fields. Now finally we'll be moving towards all calculation-based concepts that you need in order to solve mathematical questions. So first, 3 is calculating the force on a charged particle as it enters the magnetic field. Wasted my space by drawing 2 lines, but whatever. Okay, now let's say this is the magnetic field. This is 1, 2, 3, 4, and 5. Okay, let's say these are all charges. Charge, 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 and charge. Okay, let's say this is at rest, then the force would be 0. If this is parallel, force is also 0. If it's moving perpendicular, then the force is PQV. If it's moving at an angle, of theta. So this is V sine theta, V, sorry, V cos theta. So the force would be BQV sine theta. So the general formula for the force on a charged particle is F is equals to BQV. Unit is Newton, where F is equals to force, B is equals to magnetic flux, density, unit Tesla, Q is charge, Coulomb, and finally V is velocity in meter per second. Next, we have something called the velocity selector. The velocity selector works with the concept of the Hall voltage. So let me draw the diagram for better understanding. Okay, let's say this is the Hall voltage apparatus. Let's say positive field is this, negative field is this. Let's say the magnetic field is into the page. And let's say this is a positive. Okay, right. Let's say this is a positive charge, Q, sorry. Yeah, right. Let's say this is a positive charge. Okay. Now, since it is a positive charge, it will go through this, and there's going to be, okay, first it will go straight when it is undeflected. But before it was undeflected, the particle felt an electric force downwards and a magnetic force upwards. So just write Fm up, Fe down. So when electric force and magnetic force are equal, the particle is undeflected. Now to find the velocity of this particle, so what is the magnetic force? We just learned the magnetic force on a charged particle is BQV, and the electric force on a particle is EQ. Okay, from electric potential, from electric fields, because we know that electric field is equals to force per unit charge, so force is equals to EQ. This should be from your previous knowledge from electric fields, right? So Q cancels out. E is equals to BV, V is equals to E by B. Okay, unit MS, where E is equals to electric field strength, Newton per charge, V is velocity, and B is magnetic flux density. All right. Now, concept number 5. Wait, do we have space? I hope we have a lot of space. Yeah, we have a lot of space. Okay, concept number 5 is calculating magnetic flux density using Hall probe. Just so you guys know, Hall probe is the Hall voltage apparatus. Actually, since you guys mentioned it, I think I should change. Okay, never mind. I'll change it later. So using Hall probe. So what's the formula? So you have to recall a little bit of your AS learning. From AS, we learned E is equals to V by D. Okay. No, actually not. Sorry. So first of all, we know E is equals to V by D because electric field strength is equals to voltage divided by distance. From AS, we know I is equals to A and QV. Okay. Therefore, velocity is equals to I divided by A and Q. Okay. All right. Now, so uh, we can also write. So if we remember the Hall voltage, right? Right. So positive, 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 negative, negative, negative. Okay. Now, let's say the current is flowing in this direction. Plus Q. Okay. Let's say this is L, this is D, and this is T. So if we magnify it, we can say this is L, this is D, this is T. L, D, T, right? Okay, so the area of this is D into T, and volume is L into D. I mean, not volume, just dimensions. Dimensions are L into D into T. Let's label it A, B, F, E, C, D, G, H. Right. Okay. So dimensions of the hull voltage. Now we can write. So instead of, yeah, so we know that V is equals to I by A and Q, where A is the area. So current divided by, instead of A, we can write D into T, D into T, and Q. N is number of charge carriers, and Q is charge on each charge carrier. Okay. Now from A2, we know that magnetic force is equals to electric force. So BQV is equals to EQ divided by QQ cancels out. So B is equals to E by V, which is equals to V by D divided by I by uh, N, D into T, Q. Now we can cancel out this D and this D, and we are ending up with the formula V by I, NQT. Now, NQT is equals to constant provided by supplier, where B is equals to magnetic flux linkage Tesla, V velocity, I current in amperes, N is number of charge carriers per unit volume. This is just a value, it has no unit. Q is charge on each charge carrier, which is Coulomb, and T is thickness of Hall probe in meters. Now, so the funny part is, sorry, uh, this derivation came only twice, which is before 2022. Yeah, after 2022, no derivation came, only the formula came. So you guys can just memorize this formula. It's also given in your, I think, formula sheet booklet. But otherwise, I still want to write it down because this is a very important concept that most people miss. You should know how it came at least. You should have the idea. Anyways, you guys can. There's one more. Okay, okay. A concept that is similar to this is calculating Hall voltage. Now, what's funny is this is a one-line concept. Hall voltage, you can just find it by rearranging the previous formula is equals to BI by NQT, where Hall voltage is proportional to number of charge carriers. Unit is volts. Nice. Okay, let's see how many concepts we covered a lot of things. Now, we're far from done because there's, I think, there's so much more, bro. There's so much more. Okay, now we are going to find out concept number 7 is calculating force on a current carrying conductor. So we found out the force on a charged particle, but now we're going to find the force on a current carrying conductor. So again, magnetic field. Let's just draw 1, 2, 3, 4, 5. Okay, now if the current is parallel to magnetic field, force equals to 0. Okay, if current, sorry, right. Now, if the current is perpendicular, I is equals to F, sorry, F is equals to BIL. I'm not wrong. Force is equals to BIL. This is max. And if current acts at a certain angle, then this is sine theta. This is cos theta. So force becomes PIL sine theta. So as you know, so the general formula is F is equals to PIL sine theta, where B is equals to magnetic flux linkage, Tesla. When you're writing down the notes, always make sure to write what symbol means what along with its unit, because sometimes you are given 1 or 2 question marks where you have to write the units. Okay, F is I is equals to current, and L is equals to length of conductor in meters. Okay. Um, then there are a few more. Mm, A lot of space. I can work with it. Okay. So, right. Calculating the strength of magnetic field at a certain distance away from the wire. Now, let's consider a plane in which we have a wire going into the, yeah, the wire. Okay. Now let's say it is a certain distance away, just let's denote it as d. So B is strength, which is equals to, all right, the formula is I divided by 2 pi d. This, usually you don't have to memorize this formula, because if a question like this is asked, they usually give the formula to you, okay, and they expect you to use it to calculate it. All right, right, now, okay, again, B is magnetic flux density d, I is current in wire A, d is distance from wire, and this is permeability of free space, which is equals to 4 pi times 10 to the power minus 7 Tesla per milliamps. Now, this has a simplified version, which is B is equals to 24 pi times 10 to the power minus 7 times I divided by, sorry, not 24, sorry. It's 4 pi, 2 pi d, so this is crossed out, which is overall B is equals to 20 to the power minus 7 times I divided by d. It's a simplified version of this formula. Again, this is, you can choose to ignore this. You can choose to ignore this, but I think Edexcel people have this. Edexcel and AQA people have this still. But as far as I'm concerned, I think Cambridge removed it. Okay, we have, I think, 5 to 10, no, actually 5 more concepts. Hopefully we can finish it within the next 40, 45 minutes, hopefully. Okay, uh, goodbye guys. No, actually, wait, let's take a break. Hey guys. Hey guys, so let's move on to the remaining things that we have. Concept number 9. That is, right. Okay, okay. Uh, forces of attraction or repulsion between two wires. Now, even though the calculation is not required for this section, uh, the concept is. So take notes along with me. So we're drawing a plane. Okay. Now, let's say uh, two wires going into the page, wire 1, wire 2. So there it is. So the movement of current is in these directions. There, attraction. So this side forces are acting towards each other, so attractive. So these are like. Okay, like currents attract. Now, what about unlike currents? Now, let's say this one is out of the page, and this one is into the page. Then it would be like this. Okay. So force of attraction are this one, they're going opposite to each other. So you can say, wait, so we can say, unlike currents attract. Okay, so what's the force? How do we calculate the force? Okay, now if we imagine that this is, let's say, wire one, and this is wire two. Let's look at like currents, okay? So in wire one we have I1, we have I2 for wire two, and this is the length of the wires. So the general formula for the force is mu naught I1 times I2 multiplied by length divided by the 2 pi d. 2 pi d. Right. Okay. Now where? Where I1 and I2 equals to current in the wires. Uh, L is the common length of wires. D is the distance between two wires. And finally, mu is the permeability in free space, which is 4 pi times 10 to the power minus 7 Tesla milliamp per milliamp. Uh, and once again, we can have a simplified version. So simplified, sorry, simplified version would be, right, right. So the simplified version, if we just put in the values of the mu naught, then we can get F is equals to 2 into 10 to the power minus 7 I1 times I2 times L divided by D. Okay, right. Meters, ampere, and F is force, Newton. Right. Now we have a few more things left. Moving forward is, right, what is this? Number 8, I think, right? Number. So concept number 10 is magnetic flux. So what is magnetic flux? Magnetic flux is phi B into A. This is the general formula. And this is the idea of magnetic flux. Say a sheet, 1, 2, 3, 4, 2, 3, 4. Right. So the unit is Weber, WB. Nice. Now, excuse me. Right. Let's say the magnetic flux is going at a certain angle. Then it would be phi is equals to BA sine theta. Okay, now for 11, that is magnetic flux linkage. the formula for magnetic flux linkage is there are two formulas, right? That is n chi is equals to BAN sine theta, where n is the number of turns in coil. The idea is something like this. Right. So this and that this. Okay. So okay. Right. So no, I don't. Right. Let me draw it nicely. So the coils are like this. Right. Nice. Okay. So this is always of course, the general formula. Now, if right. Okay. Yeah. No. So next is where we use this formula, or where this is used is the next concept. I think I'm gonna take it up because we don't have space. Wow, we came a long way. Of course, later I have to modify it further because. Right, hold up. Give me a second. Okay, so concept number 12 is Faraday's law of electromagnetic induction. Right. So the Faraday's law of electromagnetic induction is defined by the formula E is equals to minus N d by change in magnetic flux linkage divided by change in time, which is unit is volts. Right. So this represents change in magnetic flux linkage per unit time, and minus is equals to minus is equals to Lenz's law. Lenz's law. Right. And of course, N is number of turns in coil, which is actually constant. Right. And E is EMF. EMF. By the way, when calculating the Faraday's law of electromagnetic induction, in the syllabus, it's mentioned you may or may not include the minus. If you include the minus, that's fine. But if you don't, they won't cut your marks because at the end of the day, you're just finding out the EMF, right? And as long as your value of the EMF is correct, it's all right. So EMF isn't false, right? This is, I think, Weber per units, Weber per second. Okay, right. Now, we don't have generator. You used to have generator, but we don't have generator anymore. Generator is only in our IGCSE O-level syllabus. So yeah. Okay. Now moving forward. Circular motion. Okay. So circular motion. This is a concept that's linked with our chapter 1. Okay. Now let's okay. An object that is in circular motion, its velocity is perpendicular to its force. Always. Resultant force is always towards the center. Therefore, using this concept, you can say required centripetal force is equals to magnetic force, which therefore mv squared by r is equals to bqv. Vv cancels. So we can just say, usually what they do is they tell you to find the radius. Okay. You can modify the formula and write r is equals to mv by bq. But otherwise, you can just work with this. This is your main. This is your main formula. All right. This is your main formula. Okay. Feel like this is not enough. I still want to write it down, a few points for you guys. So, charged particles in a magnetic field perform circular motion. This is true if it doesn't, if it's not, okay. This only occurs if the magnetic force is not equal to electric force. You'll find such cases where the particle only experiences magnetic force but does not have any electric force. So it is not undeflected and moves in a circular motion. Okay, perform circular motion. So okay, a magnetic field performs circular motion as velocity and force are perpendicular to each other. Okay. Concept number 14 is towards transformers. Now, I know a lot of people think this was removed, but this isn't actually removed, guys. We still have basic transformer questions in our syllabus, but majority of the calculation, I think, was removed. However, I'd still like to include it in case you guys need the concept. So, this is a transformer. Watch. Okay. Now, this is primary coil. Okay. Primary voltage. And this is secondary coil. Secondary coil and secondary voltage, secondary current. Also IP, primary current. Now, for 100% efficiency, we will have primary coil divided by secondary coil is equals to primary voltage by secondary voltage. This formula can come in many formats. For example, sorry, okay, my bad. I made a mistake. So this is the general formula for transformer. All right. Okay. This is a general formula for transformer. Now we have two types of transformer. We have a step-up transformer in which secondary coils is greater, number of secondary coil is greater than number of primary coils, and value of secondary voltage is greater than value of primary voltage. And step-down transformers in which uh, primary number of turns in primary coil is greater than number of turns in secondary coil. Basically the opposite of step up. And VP is greater than VS. And you can say that for 100% efficiency, power in is equals to power out. So VI PI is equals to, sorry, VI, uh, IP VP. IP VP is equals to IS VS. Or in ratio, we can just say VP by VS is equals to IP by IS. Now, I think I'm not going to take this side of the whole space. I'm going to bring it down here. Nice. Okay. Next concept is, all right, there's a few more. I think there's one more that's left. So, concept number 15 is force on wires due to each other's magnetic field. Now, guys, let's say that we have a wire going into the page labeled P and a wire going out of the page labeled Q. The force on wire Q is towards the right. The force on wire P is towards the left. Now, the force Q is equals to magnetic flux density of P multiplied by the current of Q multiplied length of Q, of course. Let's say P and Q have length L. P and Q have length L. Okay, and let's say the force of P is going to be the magnetic flux density of Q multiplied by the current of P into length. Now, final concept is left, which is This is going to be the final concept for oh wait. Okay, yeah, this is the final concept for magnetic field. So up till this is the final concept for magnetic field. Now, give me a minute to decide if I should continue with concept number 16 as it is, or should I make a separate column for alternating currents concept? I think I'll make a separate column. Okay, wait. Shapes. I think I saw a shape like this. Okay. How does someone reverse? Okay, I can't reverse it. How do you rotate it? Okay. Hmm. All right. Okay. I think what I'm going to do is I will. All right. No, I'll continue as it is. No, I'll give heading for alternate guard. Hold up. So line, like a separate line. I don't think we need this much space, but sure, I'll take it. And another line for this side. Okay, I'll label it alternating current concepts. Nice. Okay, now starting again. So alternating currents start with a general graph, general sinusoidal graph. Sinusoidal graphs can represent both sine graph and cos graph, so remember that. But we are going to be starting with the sine graph. So this is V voltage by voltage, and this is the angle in degrees. Okay, so this is V naught, this is minus V naught. Now the graph will look something like this, where this is 90, this is 180, this is 270, and finally this is 360. Okay, where y is equals to a sine bx plus c, where a is amplitude, b is number of cycles in 360 degrees, and finally c is the y-intercept, or also called, or also the mean value, or reference point. Okay, therefore we can write a is equals to v naught, theta is equals to omega t, and c is equals to 0. Therefore, the general formula for velocity and current will be v is equals to v naught sine omega t, I is equals to I naught sine omega t. By the way, guys, you can, if the situation commands, it can also be v is equals to v naught cos omega t and I is equals to I naught cos omega t. Depends on your question. But this is the general formula. Okay, right. Therefore, or thus, we can say power is equals to voltage into current. So P is equals to V naught sine omega t, I naught sine omega t. Therefore, V naught I naught sine square omega t. Therefore, the general formula for power is P is equals to P naught sine square omega t, as V naught I naught is equals to power. Unit watt, unit volts, unit is amp. All right. Then we have, okay, I think I can take this down a little. Sorry. This is V naught minus V naught, and the heading should be general formula of voltage, current, and power. Okay, next, so we move on to concept number 2. This is going to be root mean square voltage and current. The root mean square voltage and current is, okay. Now, if we think about this graph once again, you can say, let's draw the graph once again. Now, we can say this is V naught minus V naught. Okay, now simply let's think about the mean. Simple mean would be, no, actually, let's not say simple mean. Let's say V mean is equals to V naught plus minus V naught is divided by 2 is equals to 0. However, now if we square this value, then this graph will become something like, so as I was saying, if we square this graph, then let's just draw the graph. Oh, sorry, just draw the graph by volt. Did I add time in the other ones? But that's also right. So if we square this graph, the the sketch kind of becomes this, because negative values are turned positive. Hence what we have. Oh, this is kind of wrong. So this is wrong. It should be v squared by v squared, and the max value is v naught squared. Right. Now, if we squared it, now our mean, we have to say this as mean square voltage. Now, our mean square voltage is V RMS is equals to 0 plus V naught square by 2, which is equals to V naught square by 2. Oh, sorry, it's not VM RMS, it's VMS. So VMS is equals to 0 plus V naught square by 2, V naught square by 2, and VRMS is root of V naught square by 2. Therefore, VRMS is equals to V naught by root 2. That is the formula that we'll be working with. Of course, unit is volts. Right. Again, similarly, IRMS is equals to I naught divided by root 2. Unit ampere. Actually, I'd like to bring the snip tool, bring this here. Okay. Thus, we can say that P mean is equals to IRMS multiplied by VRMS, which is equals to I naught by root 2 times V naught by root 2, which is equals to I naught V naught by 2. And we know that I naught P naught is also P naught by 2. Therefore, P mean is equals to P max divided by 2, which is equals to P naught divided by 2. Yeah, right. Okay. Now, it's the next concept. Now, we will be looking at half-wave rectifiers. So if you guys don't remember what half-wave rectifier was, half-wave rectifier is rectifier that reverses voltage, removes voltage in one direction. Okay, half-wave rectifier. This is concept number 3. Current. Okay, so we have two things that we have to look out for, the forward bias and the reverse bias. So what does the forward bias look like? Power supply 1, power supply 2. This is a light bulb. This is positive, this is negative, this is alternating power supply. This is positive, this is negative. And this is your forward bias, letting the current flow. Forward biased. Now, the forward bias is all voltage is on lamp, no voltage on diode. Now, similarly, if we draw another one, same diagram. This is positive, this is negative. This is the lamp. However, in this case, this is the positive, this is the negative terminal. Therefore, current flow is no current flow actually, but the flow is in the opposite direction. Okay, therefore, we say this is reverse biased. Now, for reverse biased, all voltage on diode, no voltage on lamp. Right. So basically, the opposite of our bias. Now, how does this look in graph? So basically, we have, let's draw the input signal and the output signal. Okay. No, I think this is a bit too big. So this is forward, this is reverse, this is forward, this is reverse. Okay. Time second, voltage volts. So this is input signal. Now, how does the output signal look? It's a good color, this is. Now, for output signal, the graph will look something like this. So do you guys remember what I said? I said that for half-wave rectification, voltage in one direction is removed. Therefore, the reverse voltage is removed. Okay, to mention one point, that is rippling direct current with lag. There's some lag because of these regions, which are smoothed out with 0. Says volt by volt time second. Output on lamp. All right. Now, of course, this is very inefficient because the lamp will blink and then stop. The lamp will light up and then stop, and then light up again and then stop. So how did we fix this? How did people from the ancient ages figure out a way to solve this problem? Which leads to our fourth concept, full wave rectification. In full wave rectification, voltage in one direction is reversed. So this is what a bridge. So the main thing that they used in full wave rectification is a bridge rectifier. Watch. In bridge rectification, there are 4 diodes. Okay, this is 1, this is 2, this is 3, and this is 4. 4 diodes that help to change or that help to reverse the direction of voltage. It's called bridge rectifier. Now, for positive half cycle, right? So, okay. So let's give some color to it. The positive half cycle. Okay. Now, again, guys, these are mostly drawings. Without drawings, I can't really help you understand. Okay. So let's draw. This is the power supply. So the bridge rectifier first. 1, 2, 3, 4. So this is 1, this is 2, this is 3, and this is 4. This is the resistor. And wait, wait. This is positive, negative. Again, alternating power supply. Now, okay, the load resistor as an extension to this point, which makes it like this. Okay, now we have to figure out. Now let me explain how the bridge rectifier works. So when current goes out, so since this is alternating power supply, in one instance, plus is in on top, and on one instance, the plus is going on bottom. So when the plus is on top, this will be the movement. Current will move from this side to from this to this side to this side to this side. Therefore, this is the positive terminal. Goes through the load resistor. This becomes the negative terminal. And if we continue our path, goes here. It travels up this line, goes down this line, and finally onto the negative cycle. So this is the positive cycle with for bridge rectifier. Now, give me a moment. Now let's look at the negative half cycle. Negative, negative half cycle. Okay, so the negative half cycle, the diagram is the same. The diagram is the same, but I have to draw it again. So let's draw the bridge rectifier. One, two, three, 4. This is alternate power supply. Okay, and load resistor. Okay. Now, how does the negative terminal work? The negative terminal, as I said, in this instant, negative is going to go up, positive is going to go down. So the direction, now, it begins from this, goes down to the right, to the top, then goes here. This becomes positive, moves down, becomes negative, this becomes negative, moves left, moves to the top. Oh, okay, my bad. I think I should have to, let me just cut this out. Yeah, moves up top, the signal, the flow moves top, and then travels through here, and finally returns back to the negative terminal. So this is the negative half cycle. Right. Okay, we have a bit more left. Oh. Okay. So, all right. Now, how are we going to represent this in a graph? Similarly, we have to draw graphs once again. So the input signal looks like a normal sinusoidal graph, which is like this, right? This is the input signal where the positive half cycle is this side and the negative half cycle is this side. Okay. Now, how does the output look like? The output graph, oops, yeah, the output signal looks like this when you use a bridge rectifier. So once you have used a bridge rectifier, the graph will look like this. Mm, The voltage in both directions is reversed. In all directions is reversed. So if you, this is the positive cycle, and this is the negative half cycle. Again, you have to mention that it still is rippling. It still is rippling with, or no, just don't rippling with, just rippling DC. Rippling DC. This is because you still see that voltage is still dropping to zero and then climbing up, even if it doesn't. Even if there is no flat line, there's still a drop in zero. Right? This is still zero. So how do we fix this? We somehow have to smooth it out so that okay, the scientists who worked with the bridge rectifier found that the lights that we were using still blickered, even though the blickering wasn't for much long. Okay, like that, even though there was no flat line. Okay, let's say light is on, light is off for 2 seconds, light is on, light is again off for 2 seconds. Now, for this is half wave rectification. In full wave rectification, they saw that light is open, light is open, but then light stops for 0.2, 0.3 seconds, opens again. Again stops for 0.2 seconds, again. So they were like, how do we fix this? Right. Mm, okay. Light off. Light off. So they came up with a solution. They used they used a capacitor. Now, I'll explain why here. I think I should not go much further up. Yes, I will explain concept 6 here. Smoothing. So, in the same diagram, what they did was they used a capacitor parallel to the load resistor. Just watch. Now, so this is the load resistor. What they did was they added a capacitor parallel to the load resistor for charging and discharging. So, how did the graph look? This was a generational success. It was a generational success that changed history as we know it, the history of electricity. Okay, so this is the graph, volts, volts. Now, let's time second. So now, we saw the graph be like 1, 2, 1, 2, 1, 2. Right, this was the graph. Sadly, this is not what happened. The experiment was a success, and what the capacitor did was, wait, let me show you. The actual graph was something like this, from 0 to a certain drop, certain drop, certain drop, certain drop. There was not, okay, wait. Mm, wait. This is the new graph. So as you can see, the voltage never fell to zero. The voltage never fell to zero due to discharging. From this region to this region, there was discharging. And this region to this region was charging. The discharging caused the voltage to smooth out. Uh, hence, what happened? The light bulb, it's always stayed on, but for example, when the voltage dropped, you'd see the intensity of the light would drop. Nowadays, the modern LED lights and the lights that you see in your living room, they have little to no charging. Discharging is at maximum. Voltage drops by 0.01 volts. So there is little to no change. Okay, so right now I'd like to add one more thing. That is the current nowadays bulbs have even smaller discharging like this. Okay, now how did scientists do this? Very simple. We figured it out that what you can do is you can decrease the gaps with greater value of capacitance. Right. So if you have a capacitor with a very large value of capacitance or many capacitors parallel to each other, then you will have a lot of discharging, so the lights will always stay on with little to no dim. Okay. I'd like to draw a bit more to the concept. So for this is the light bulb on, off, and on again. Right. Just let me give it some color. Okay. Now for discharging, what happens is what you see is light, light. So out of three examples, like three, this is a bit bad. So, so you can see that the light has a lot of intensity. This is small intensity, low intensity, and again a lot of intensity. Intensity can be shown with deeper color. So let's say light has a lot of color, but then again the color is going down, I guess. So no, actually, okay, yeah, this concept goes here. So at right, so at these sections, the light looks like this, and in these sections, the light were like this. The color dims down. Bright, so I'll call them bright, dim, bright. I have a feeling I got the color wrong. Yeah, I did get the color wrong. Bright color should be yellow. Yellow, and this should be orange. Dim should be orange. However, with modern technology, the lights always have, there's no dim, in simpler words. No dim in modern lights. Okay. Uh, okay. On, off, on. So this section lights are on, and this section lights are off. Light off for 0.2 to 0.5 seconds. Very small, considering that this was the late 1700s, early 1800s. However, with this, we are done with part 2. I'm sorry, guys. I wanted to make the video a lot shorter. However, I think this was very important. Like, we covered 5 more topics of great importance. I'll see if I can fast forward some sections, but if I can't, again, please bear with the video and go through them. So yeah, thank you for watching and stay tuned. I'll see you guys for part 3 with quantum physics, nuclear physics, medical physics, and astronomy, inshallah. Bye bye.